Okay, I think it's going. I haven't made one of these in a while because my other computer's been down. But this is for principles, so I wanted to talk a little bit about making some of the threaded connections in the rapid prototyping machine, in the fuse deposition modeling machine. So for those who are not in the class and just happen to be watching this video, we're talking about making some components in a 3D printer that's creating an ABS part using this fuse deposition modeling. It's a Stratasys, like, dimension 3D print or something like that. It's a pretty typical one. So in this project, there might be some desire to make threaded connections, and so I tried to make a set of parts, basically a lead screw and a nut to go on it. So in doing this, I figured I'd first take a stab at doing the Acme threads. So we've talked about this. Let's see if I can get this on here. Sorry for being low tech, but I can't really get the whole board on there. So when I look at the Acme threads, and I posted some of this stuff from Machinery's Handbook on the Blackboard site. First I tried making the sort of a conventional Acme thread geometry, and what you find is for shafts about this dimension, where we might be looking at for this gripper project, the thread width is pretty small and probably not what we want to. It would have a lot of difficulty in fabricating in the rapid prototype machine. So I modified the geometry. It's a little non-standard, but it's basically a 60-degree pitch, 60-degree face angle, and it's about a 1/4-inch pitch. And the important thing is, ignore my phone, is that the clearance diametrically is 20 thou. So I kept it at 20 thou. And you can see here, basically, that's the clearance we're talking about there, okay? That's 20 thou diametrically, both on the crown and the bottom. And that actually seems to work pretty well. So you really, if you look at the, let's see how good I can put this up here. Will it do it if I back off? No, it's not going to focus that well. But obviously these parts were grown in this orientation. So you see the stepping, rastering through this depth here. And what that means is on the tops, we kind of have like a flat, and then better rounding on the sides, but a more exaggerating stepping on the top and bottom. Also, if you look, I should probably hand this into class. Let's see. I think if nothing else, you can see, even though it's not focusing very well, if you look real close, where my hair isn't, that there is some jaggedness in the internal thread as well. So with the 20 thou clearance, when I first put it together, I really had to force it to get it through, and that's because there was a lot of flash on here. But then actually I went to a very boring meeting, and I spent the past hour of that meeting just kind of working the screw back and forth. And actually what you can see is that it seems to do pretty well. It threads from both sides completely through. I mean, it's not as good. There's still a lot of sliding friction. I can't really spin the nut out. Well, actually, it's not too bad, actually. Let's do it this way. Let's get the right direction. It doesn't really spin out like it would if I had a well-machined metal lead screw, but it's not bad, okay? So I think that's what I'd recommend. If you want to keep the pitch such that it's like at least a 1/4-inch pitch, the 60-degree face angle is not bad, the tooth angle, but I think the important thing is to have at least 20 thou diametric clearance, maybe even a little bit more, maybe 20, 25 thou. And as the more I work this, I'm getting a little slop in it too, but I think that's pretty reasonable for our needs, okay? All right.